Hi guys, welcome to Budget Power Electrical Solutions. In this episode, we are going to look at what actually happens to motor current from the moment we press the start button until the motor reaches its normal running speed. You may already know that a motor can draw a very high current during starting, and then within a short time, that current comes down significantly. But why does that happen? What is actually changing inside the motor while the rotor is accelerating? In our previous 2 episodes, we discussed some of the important basics of motor overload protection. In this episode, we are going to connect those ideas with FLA, starting current, locked-rotor current, RPM, and back EMF. Once we understand how all of these are related, it becomes much easier to understand why an overload relay behaves the way it does. So, before we talk about high starting current, let's begin with our main reference point. What exactly is FLA? Let's start with FLA, or full load amps. FLA is the current the motor is expected to draw when it is operating under its rated conditions and carrying its normal full load. This is one of the most important values you will find on the motor nameplate. In practical electrical work, we use FLA as a reference when we check motor current and when we select or adjust overload protection. But here is the important question. If the motor normally operates around its full load current, why does the current become several times higher when we first start the motor? To understand that, we need to look at the motor at the exact moment the rotor is still stationary. That brings us to locked-rotor current, or LRA. Now let's look at what happens at the exact moment the motor starts. When the contactor closes, supply voltage is applied to the motor, but the rotor is still stationary. At that instant, the motor speed is 0 RPM, and the current can rise to a very high value compared with normal running current. This is where locked-rotor current, or LRA, becomes important. LRA represents the high current condition associated with a stationary rotor. It is not the normal operating current of the motor, and under a healthy start, the motor should not remain in this condition for long. As soon as the rotor begins to accelerate, the electrical condition inside the motor starts changing and the current begins to fall. So next, let's compare FLA, starting current, and LRA together and see how they fit into the same starting process. Now let's compare these 3 current values together. FLA, or full load amps, is the current the motor is expected to draw when it is operating under its rated conditions and carrying its normal full load. Starting current is the higher current the motor draws while it is accelerating from 0 speed toward normal running speed. And LRA, or locked-rotor amps, is associated with the condition where the rotor is still stationary. The important point is that these are not 3 completely separate ideas. They are all connected to the same motor starting process. At the beginning, current is very high. Then, as the rotor starts turning and speed increases, the current gradually begins to fall toward the normal running value. So the next question is, what is changing inside the motor as RPM increases, and why does that cause the current to come down? That brings us to the relationship between motor speed and back EMF. Now let's look at why the current starts to come down as the motor speeds up. At the moment of starting, the rotor is stationary, so the motor has very little opposing electromagnetic effect. Because of that, the current is very high. As the rotor begins to accelerate, the motor develops more back EMF, or opposing voltage. As back EMF increases, it reduces the effective voltage driving current through the motor windings, so the motor current begins to fall. So in a simple way, we can remember it like this. Low RPM means very high current. As RPM increases, back EMF increases and current decreases. But this change does not happen instantly. The motor needs time to accelerate from 0 RPM to its normal operating speed. So next, let's look at the complete starting sequence step by step. Now let's follow the motor starting process step by step. When we press the start button, the contactor closes and supply voltage is applied to the motor. At that moment, the rotor is still at 0 RPM, so the motor draws a very high starting current. The motor then develops starting torque, the rotor begins to turn, and the motor starts accelerating. As the speed increases, back EMF increases, and the current begins to come down. Finally, when the motor reaches its normal operating speed, the current settles closer to the value required by the mechanical load. So now let's put some real numbers into this process and look at a 60 amp motor example. Now let's use a practical example. Suppose we have a motor with a nameplate FLA of 60 amps. For this example, let's assume the motor draws about 6 times FLA at the instant of starting. So 60 amps multiplied by 6 gives us approximately 360 amps. That does not mean the motor will keep drawing 360 amps. This is only the high starting current at the beginning of acceleration. As the rotor picks up speed, the current starts to come down, for example, from around 360 amps to 240 amps, then 150 amps, then 90 amps, and finally closer to the normal running current around 60 amps. The exact values can vary depending on the motor design, supply voltage, connected load, and starting method. So next, let's look at this same starting process on a graph and see how current, RPM, and time are all connected. Now let's look at the same starting process on the graph. At the very beginning, motor speed is 0 RPM, and the current is at its highest level. As time passes, the rotor accelerates and RPM begins to increase. At the same time, the motor current starts to come down. So during a normal healthy start, we can clearly see this relationship. RPM goes up while current comes down. Now think about what happens if the motor cannot accelerate properly because of heavy load, low voltage, or a mechanical problem. The current may stay high for much longer than normal. And that is exactly why overload protection becomes so important. So next, let's look at why the overload relay does not trip immediately every time the motor current rises above FLA. Now we can understand why the overload relay does not trip the moment the motor current goes above FLA. During a normal start, the motor may draw several times its full load current for a short period. If the overload relay tripped immediately every time that happened, the motor would not have enough time to accelerate to normal speed. So the overload relay looks at both current and time. A high current for a very short period may be normal during starting. But if that excessive current continues for too long, the motor can overheat and become damaged. That is why overload relays follow a time current characteristic rather than acting like an instantaneous short-circuit device. So next, let's apply this idea practically and look at how we would approach the overload setting for our 60 amp motor. Now let's apply everything we've discussed to the overload relay. For our example, the motor nameplate FLA is 60 amps. So the first step is to choose an overload relay with an adjustable current range that includes 60 amps. Then we set the relay according to the motor nameplate data and the manufacturer's instructions. The important point is this: we do not set the overload relay based on the high starting current, such as 360 amps. That current is temporary and part of the normal starting process. The overload relay is mainly there to protect the motor from sustained overload and overheating. It is not the same as short-circuit protection. So now, in the final slide, Let's bring the whole idea together and summarize the motor current from start to normal running. Now let's bring everything together. We started with FLA, which is the motor's normal full load current under rated operating conditions. Then we looked at starting current and LRA, where the motor can draw several times more current while the rotor is still stationary or accelerating. We also saw how, as RPM increases, back EMF increases, and the motor current begins to fall toward its normal running value. And this is exactly why an overload relay does not trip, simply because the current rises for a short time during starting. It looks at both how much current is flowing and how long that current continues. So if you understand the relationship between FLA, LRA, starting current, RPM, back EMF, and trip time, overload relay operation becomes much easier to understand. Thanks for watching Budget Power Electrical Solutions. If you found this useful, subscribe for more practical electrical and motor control videos.